The chart we're looking at now shows the early life history of a planet from birth and the relative masses of Mercury, Venus, Earth, and Jupiter. And at the bottom it says, planets are born, grow to maturity through generative preponderance, then fade and die through radiative preponderance. All form appears and disappears by the same process. It must be recalled that the expansive force of repulsion is also exerted from within, consequently accelerating rotation. It is as though the planet were rotating with the aid of a propeller with its shaft turned toward the local west. The direction of rotation of a planet gradually changes in reference to its local direction, but never changes its universal direction. Its local direction of morning at birth is not its local direction of evening when it has aged. In the morning of a planet's life, the sun dominates it through its north charging pole. Its local east and west are therefore those with which we are familiar on this planet, and the direction of rotation of the sun is counterclockwise in reference to an observer located north of the solar system. At the planet's noon of maturity, the sun rises and sets in the plane of the planet's equator. Its local east and west are therefore in the plane of the sun's rising and its setting. In the planet's evening, the poles reverse their position. Its local east and west are therefore the reverse of those at birth, and the direction of rotation is clockwise in reference to an observer similarly located. During its entire period, it never rotates or revolves in any other direction than the expanding direction of centrifugal force, whichever draws away from north in the direction of north's expansion, the west which leads to south. The rotation of a planet in space might well be likened to the rotation of a ball when rolled upon the floor. The greater friction of the high potential of the floor causes a greater resistance to the motion of the ball than the lesser friction of the low potential of the air, which impacts against the upper surface of the ball. The planet rolling along the floors of space is resisted in exactly the same manner by the difference in friction between the higher pressures impacting against its inner surface and the lower pressures impacting against its outer surface. The equator of a ball rolling across the floor, propelled by a dead center blow, will always be in contact with the floor, and the pole of rotation of the ball will always be parallel to the floor. This is because the conditions of resistance remain constant. Resistant pressures which cause the rotation of a planet are not analogous to that of the floor and the ball, when propelled under such conditions. The resistance not only is greater against the surface of the planet which is toward the sun, but also against that hemisphere of the planet which is toward the ecliptic plane of the sun. Conversely, the resistance is less against the hemisphere which is away from the sun, and also that one which is away from the ecliptic plane of the sun. The former state is preponderantly inductive, and the latter is preponderantly conductive. The greater the resistance to an action of force, the greater the general activity. The greater the general activity, the greater the power of mass to absorb heat. The less the resistance to the reaction of force, the greater the radioactivity. The greater the radioactivity, the greater the power of mass to give out its heat. A planet or satellite can only rotate true when its equator is exactly in the plane of the solar or planetary ecliptic. In this position it is exactly analogous to the rolling of a billiard ball which has been projected without any English. In this position, its pole of rotation is at an angle of 90 degrees to the plane of the equator of its primary. When in this position, a planet's polar magnetic base has contracted into disappearance so that its electric pole and its pole of rotation coincide. Also, the equatorial planes of primary and planet coincide. When in this position, its gravitative center of north is a point of no dimension, and its radiative center is in a plane which measures the diameter of the mass. When in this position, the diameter of the equator is equal to the diameter at the poles. This position is only possible at the ecliptic of the wave where generation ends and degeneration begins, and for new planets and satellites at the ecliptic focus of a system for their mass, where their youth ends and their age begins. All mass rolls along the floors of space upon that part of its surface where radiation is at a maximum. The blow which gives the impetus to the planet is struck from within exactly in the plane of its ecliptic, the plane of maximum discharge. The resistance to that blow is greatest at the charging poles, the points of maximum charge. As the plane of maximum discharge and the points of maximum charge change constantly during a planet's life period, so must the planet therefore constantly change its position in relation to its primary. As the ecliptic area expands and its charging poles draw away from their poles of rotation, a planet gradually turns upside down. It then appears to rotate in the opposite direction. Suns give birth to planets and planets to satellites until just before they have perfected their spherical form. Planets are born from sunspots which are located some degrees from the solar equator. After birth, they continue to generate during their brief youth. During this period, they draw ever closer to the focusing point of their particular mass in the solar ecliptic areas until the equatorial plane of the mass coincides with the solar equatorial plane. For any matured mass, the focusing point in the solar ecliptic area is always in the plane of the solar equator, its distance from its center of force depending upon its relative mass. This position marks the end of the young planet's preponderantly generative period and the beginning of its preponderantly radiative period. From this position, the new planet gradually recedes as it gradually expands and tilts its poles as a consequence of its expansion toward its parent and then away from it until it has reversed its natal position. One rotation of a planet is 1 day of a planet. It is the standard unit from which the hours, minutes, and seconds are derived. After determination of the relation of a planet to that of the Earth as a standard unit, the day of any planet may be determined by a calculation in universal ratios. With the knowledge of the potential position of any planet as indicated by its relative distance, plane, and revolution period, its rotation period can be as easily calculated as its relative mass. Distance, plane, and revolution periods are easily determinable. Other dimensions are very often impossible to ascertain. At present, we can determine the periodic day of a planet by observing the return of markings visible on its surface. The days of Mercury, Venus, Uranus, and Neptune would be forever beyond our exact knowledge without the ability to calculate potential positions and without the law of universal ratios, for there are no visible, dependable markings on these planets. The period of rotation of smaller planets such as Ceres and Eros would also be hopelessly indeterminable without the aid of this law. The rotation period of either a planet or satellite when near its gravitative radiative center is so long that such a mass always keeps the same surface toward the center.